So now we are going to look into the conical capacitor problem which we saw in the earlier modules of finite element method. We are going to do the same problem using algebraic topological method, and we will follow the same pattern what we have done for the parallel plate capacitor. So without much ado, let us go into the code itself. So the code is going to solve for the conical capacitor. So now we are going to use this problem, and let us set the value for maximum and minimum edge sizes as 0.5, and we have a problem geometry that is coming directly from a commercial solver. We can also use simple solvers to create a model geometry. So our problem is going to have this geometry. So the top plate and the bottom plate are going to be in this manner, but there is going to be a conical thing at the center of the top plate, and it is going to have a tapering, and it is be a cone. You can imagine that there is a cone and it is a circular thing, and it is having a dimension, and if you see this in the 2D, what you will see is something like this. This is a problem that we simulated in the case of the finite element method, but the 3-dimensional case will be having a kind of a cone at the center. So you can see that problem figure as follows. So this is the dimension of the problem what we are interested in, and when we run it, so this is going to be our problem dimension, and there is going to be a cone on the top which is going to come like this. So let us run the code and see how the problem is being replicated. We are going to do the same thing what we have done in the parallel plate capacitor. Initially we are going to go and do the various aspects of the primal and dual grid. You see that we are starting with 10,750 like the way we did before, and the primal surfaces and primal edges are as follows. We are extracting the data of surfaces connected to each of the edges, and we are going to compute the value of A1 and A3 matrices for the primal and the dual grid as follows. We will see the final graph for the potential in a second. So we are going to have the minimum edge length as 0.9 in order to make the code run a little faster, because then we will have little number of elements in the case. So we will set it to 0.9 to show the proof of concept, but you can go for finer discretization at later stage if you want to run the code for yourself. So let us run the program and see what is happening. So there are totally 2020 nodes, 9173 primal volumes, and the number of primal surfaces is 19,256, number of primal edges 12,102. We are extracting the data so as to create the A1, A2 and A3 matrix, which are nothing but the connectivity matrix. We are able to solve the problem and we are able to get the result as we expected. So in this case our problem geometry is having the cone at the bottom and the 0 voltage is applied on the top. This is the same thing as doing it the other way around. Top part is 1 and the bottom part is 0. So let us look at this problem here once more. In our case what we have done is we have just tilted the problem this way. So the bottom part is going to be at 1 volt, phi equal to 1 volt. The top part is going to be at 0 volt. We did that so as to change the problem slightly for us to compare the results. So what we see is, we see that clearly there are good replication of the conditions that we have given. If you see the cone is sitting here and its value is going, so there is going to be a equipotential surface, and what we also notice is as we go closer and closer to the top plate, which is in this case at 0 potential, the equipotential surfaces are no longer curved, they are almost parallel. I would like you to program your own algebraic topological method codes so as to test various problems. Simple problems like this helps you understand how to compute A1 matrix, A2 matrix and A3 matrices for a primal grid, and similarly the counterpart for the dual grid, and how one can extract the information so as to compute a simple Laplace equation. So in this case we did the divergence of D equal to 0, and in the case of the finite element method we did a Laplace equation where we solved for the del square phi is equal to 0, and this is more or less the same problem, only thing is the way we approach the problem is different. In the case of the finite element, what we did is we started with directly the Laplacian of phi equal to 0, whereas in the case of so we did the finite element approximation and we computed the potential, we computed the electric field, so on and so forth. In the case of ATM, so this is the FEM approach. In the case of ATM, we started with the primal grid. So we got the A1, A2 and A3 matrices, and using that we computed the same counterpart for the dual grid. We got A1 tilde, A2 tilde and A3 tilde. The reason for going for this is, for a problem like this, divergence of D equal to 0, we can transform this into divergence of E equal to 0, and this can be transformed into divergence dot gradient of phi equal to 0, and this is the dual grid and this is the primal grid. So we have A3 dual dot A1 of phi equal to 0, and this is the A matrix operator and this is phi. We applied the boundary conditions to compute the value of phi inversing the A matrix. That is what we have done, and what we have done also in the code is to see how long it takes for you to compute the result. We have the feeling that once you get a good understanding of the basics of the algebraic topology, coding such problems is not going to be very difficult, but of course these are for advanced learners. I would not force you to learn algebraic topology if you are not interested in the computational electromagnetics as your main research area. If it is going to be only a topic that you are interested to know, you do not need to go and code it, but if you are a person who is interested in comparing methods, to know about the value of certain method versus other, algebraic topological method is a very good tool for you to compare methods, see accuracy, and also compare what is good and what is not good with finite element, so on and so forth. So with that being said, I would not force you on learning this particular program, but for people who are interested, we encourage you to test the code and practice for yourself, and also see how the primal grid is constructed, dual grid is constructed, and how one can compare and compute the values that we are interested for practical problem solving. Thank you.